This class is recorded. I'm going to make you presenters. So 接堂好 and Kara. Xiu Yu. All right, anyone like to start? Yeah.
This is 5.32. The time x in minutes between customer arrival at a bank is exponentially distributed with mean 1.5 minutes. Part A, if a customer has just arrived, what is the probability that the customer will arrive in the next 2 minutes? So since the random variable x represents the time between blah, 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 we just interpret x to be the wait time. For part A, we're looking for the wait time that is more than 2 minutes. So within 2 minutes, there's nobody comes. So part A, P of x squared. Oh, wait. So since we have mean 1.5, and in the exponential random variable, we have equal to 1 over lambda, the expected value of a exponential distribution is equal to 1 over lambda, and is equal to 1.5 is 3 over 2. So we just do some computation. We got lambda equal to 2/3. And then we go to part A. We have the wait time is more than 2 minutes. We have x greater than 2. That's sound like 1 minus p of x less than or equal to 2. And for this, we just plug into this. So we have f of 2 is equal to 1 minus e to the lambda times 2, and the lambda is 2/3, negative 2/3. I mean 2/3 is negative lambda times 2. And at the end we got this. And for part B, what is the probability that no customer will arrive within the next minute, given that no customer had arrived in the past minute? Okay, so given that the first minute has nobody comes, and then we got calculate the next minute, the probability that no customer comes in the next minute. So it will be x greater than 2 and x greater than 1. The intercept would be x greater than 2 over x greater than 1. And we do the same step like this. We got this on the top and this on the bottom. And then we got this final answer.
Great. Good review of exponential distribution. Thank you.
Thank you.
Who's next?
Hi, Professor.
Hello.
Okay, so I'm presenting 5.38. If x is a uniformly distributed on point 1,5, find part A, the probability density function of big Y equals to log x. And for part A, we first do the CDF, the cumulative. and we know that probability big Y is less than or equal to Y, and then we convert it to we know that log X is the big Y, so probability that log X is less than or equal to Y is also equal to probability X is less than or equal to e to the exponent Y, because we converted from log X to e to the Y. So then we set up the integral that lower limit is 1 and the upper limit is e to the y power, and then 1 minus 5 minus 1 dy, which gave us the result that is 1/4 times e to the y power minus 1. And to get the probability density function, we take the derivative and we got e to the y power over 4. And for part B, we to figure out the probability that 1/3 is less than big Y less than 2/3. And since we know that the big Y is log X, we want to know what it is in X. So we have probability that e to the 1/3 is less than X and less than e to the 2/3. And then we set up the integral to that lower limit is e to the 1/3 and upper limit is e to 2/3 of 1 minus 5, 1 over 5 minus 1 dx, and then which give us the result that the uniform distribute is 0.1380.
Great. It's a review for uniform distribution. Nice. Thank you, Catherine. Who's next?
Hi, Professor. I'm going next.
Okay, great.
Can you see my screen?
Not yet. It's coming up, I think. Yes, now.
Okay. I'm going to present question number 5.34. Jones figures that the total number of thousands of miles that a racing auto can be driven before it would need to be junked is an exponential random variable with parameter 1 over 20. Smith has a used car that he claims he has been driven only 10,000 miles. If Jones purchases the car, what's the probability that she would get at least 20,000 additional miles out of it? Repeat under the assumption that the lifetime mileage of the car is not exponentially distributed, but rather is in thousands of miles uniformly distributed over 0 or 40. We consider that Jones figures that the total number of thousands of miles that an auto can be driven before it would need to be junked is an exponential random variable with parameter 1 over 20. Smith has a used car that he claims has been driven only 10,000 miles. It is given in the question. So consider x is the random variable that represents the number of miles that can be driven before being jumped. So here we will use exponential distribution. We know that the car has been driven 10,000 miles and we want to find the probability that it will last an additional 20,000 miles. We will use the memoryless property of exponential distribution where t is equal to 10,000 and s is equal to 20,000. So probability x greater than equal to 10,000 plus 20,000 given x greater than 10,000 is equal to probability into x greater than 30,000 intersection x greater than 10,000 over probability into x greater than 10,000, which will be equal to x greater than equal to 20,000. So after we know the formula, which is integral upper limit is infinity over lower limit is 20 1 over lambda exponential, and then we will put the value of lambda which is in the question that is 20. So after putting the value and solving the formula of, after applying the formula of integral, we will get 1 over 20 into minus exponential raised to the power minus 1 over 20 x over 1 over 20, and the limit infinity over 20, infinity, and the lower limit is 20. After putting the limit, we will get that exponential raised to the power minus 1, which is equal to 0.3679. And for the part B, in which we have to find the uniformly distribution, if the lifetime mileage of the car is not an exponentially distributed, but rather is uniformly distributed over 0.40. So for uniform distribution, we have the formula probability into x greater than 30 given x greater than 10, which is equal to probability x greater than 30 over x greater than 10. Then we will insert the function here, which is upper limit integral upper limit 40 lower limit 30 function dx over integral 40 and 10 function dx. And we will put the simply values and solve the integral and get the answer 0.33.
Very close, huh? One is 36, 37% is 33%.
Yes. Yes.
Nice. Yeah.
Thank you.
Thank you. Thank you. Mm. Come. Okay.
Hi, everyone. Okay, so in this problem, we were given a stock price given by S, and it either goes up or down with by a factor of 1.012 if it's up, or down by becomes 0.990 with probability 0.52. And so basically this is a binomial distribution because P is around 0.5 and N is large. And let's go to the next slide.
What
This
is the U
example.
there? Excuse me, Tom. U equals 1.012.
That's the amount that's going up. So like, let's say.
Oh, the price going up. I see.
Yeah.
Going down that
Basically,
much. Going up that much.
Yeah.
Going down 99 cents.
Mm-hmm.
So P probability or probability is upwards, going up with probability P, right?
Mm-hmm.
Okay.
Yeah. And so the question is, assuming successive independent movements approximate the probability that the stock's price will be up at least 30% after the next 1,000 periods. This is an example from the textbook. It's kind of similar. This is a normal distribution to approximate the binomial. Anyway, first we need to find the minimum number of days the stock goes up in order for the price S to increase to 1.3S because it's 30% up. So let X equal the number of days the price goes up. So the equation to find X is S U to the X D to the 1000 minus X is greater than or equal to 1.3S. So just using some random rules, we eventually get to X equals 469.20 days. And we're looking for the minimum days for S to be 1.3. So we find the next integer value. So that's 470 days. So X. Now we need to find probability X is greater than or equal to 470. And to improve our results, we use the continuity correction, where if x is greater than or equal to 470, we subtract 0.5 to improve our result. And eventually we get 1 minus p x less than 469.5. Then we use the phi, the table for the normal curve values,
Standard
which is on
norm.
page 2. And we get a negative value, so we have to do 1 minus phi, the positive value. So we get 0.0007. And then finally the probability was 0.993.
Almost 100%, huh?
Mm-hmm.
Interesting question. All right, thank you, Tom.
Can you see my screen?
Yes, show you.
So I'm going to present 5.41. Suppose that x has a beta distribution with expected value of x is equal to 1 over 9 and variance of x is equal to 1 over 81. Find the parameters a, b corresponding to x. So in this question, we use two formulas. One is the expected value of x, which is equal to a over a plus b, and the variance of x is equal to a times b over a plus b squared times a plus b plus 1. So by the question, we know that the expected value, which is equal to 1 over 9, and the variance of x is equal to 1 over 81. So first, in the equation 1, I times a plus b both sides, then we get a plus b over 9 equal to a, then times a both sides, which we get a plus b equal to 9a. So minus a both sides, which is equal to b is equal to aa. So use b equal to aa into the equation 2, which is 1 over 81 equal to a times aa over a plus aa squared times a plus aa plus 1, which is equal to 1 over 81 equal to a times a squared over 9a squared times 9a plus 1. Then just make a calculation like cancel a squared and cancel the parenthesis and times 729a plus 81 both sides and times 81 both sides. Then we will get the final answer. A is equal to 7 over 9. So just use a equal to 7 over 9 into the equation 1. So then make a calculation, we will get b is equal to 56 over 7. So the answer is 7 over 9 comma 56 over 7.
Great. Beta distribution.
Mm-hmm.
Yeah. Okay, nice. Thank you. I think Hall is the last one, Hall.
Question 5.26. Two
Okay.
types. Yeah. Two types of coins are produced at a factory. A fair coin and a biased one that comes off heads 55% of the time. We have one of these coins, but do not know whether it's a fair coin or a biased coin. In order to ascertain which types of coins we have, we shall perform the following statistical tests. we shall toss the coin 1,000 times. If the coin we
Oh,
shall conclude that it is a biased coin. Whether if it lands on heads fewer than 525 times, then we shall conclude that it is a fair coin. If the coin is actually fair, what is the probability that we shall reach a false conclusion? What would it be if the coin were biased? For the fair
nice.
coin, yeah.
Yeah, it's a nice question.
Okay.
Yeah.
For the fair coin, since we are like tossing the coins 1,000 times, so we get n equal to 1,000, and then for fair coins, have chance of getting heads and tails. So the it's the same. Then we just plug into the binomial distribution. Then we solve this one to get 1.5491. Then calculate the z-scores of this one to get 0.0606 as a result. Then we go to the bias coin. It says that I got like 55% for heads, so p go to 0.55, and we know that p plus q equal to 1, so we subtract that number. Then again apply the formulas of the distributions. We get the result of negative 1.6209, and then finding a z-scores to get 0.05252.
Interesting question. Okay, thank you, Hao. By the way, I used Hao's exam as a solution set. All his answers are correct except 8. So the number 8 is a hypergeometric. All right, anyone else like to present today? Yeah, if some of you want to talk to me about your exam, let me know, okay? We can talk about it afterwards, after class. And some of you, I'm kind of worried about you. But most of you have done so well. What was the class average? That's a good question. I didn't really calculate. Let me see. Probably, I would guess about 70. 60 something to 70, I think. Okay, I think those of you who kept presenting, kept a presentation going on, were doing really well. Because the exam was interesting. Because when I doing grading, I don't have to download your work, but somehow housework was downloaded onto my computer. Once I finished grading, I was not able to see your exam anymore. It's very interesting to me. I don't know how to, I cannot find them anymore. Okay, so we're going to talk about chapter 6. So first, let's see, what do I need to talk about in chapter 6? Let me go to syllabus just to make sure. Okay, bivariate random variable, we need to talk about joint distributions, covariance, correlation, independent random variables, sum of independent random variables, convolutions, functions of random variables, change of variables formula. All right, joint distribution, that's section 1, independent random variable, section 2, sum of independent random variable, section 3, which including identically distributed uniform random variable, gamma random variable, normal random variable, Poisson and binomial. Then conditional distributions, discrete case. I guess we don't have to talk about this. So we will finish order statistics, joint probability, and exchange random variable, interchangeable. Where is the change variables? I guess it's exchangeable random variables. Okay, probably we're going to skip 6.4, 6.5, 6.6. Then talk a little bit about 6.7 and 6.8. So that's for chapter 6. All right. Then after that, for chapter 7, then chapter 8. Okay. Let's go to chapter 6, section 1. Okay, quite long. Same rule. Okay, anytime if anyone has any question, feel free to stop me at any moment. Joint distribution functions. So far we have concerned ourselves only with probability distributions for single random variable, x. So however, we are often interested in probability statements concerning 2 or more random variables. So in order to deal with such probabilities, we define for any 2 random variables, x and y, the joints will define joint cumulative probability distribution function x and y by this. All right. So we used to deal with f of a, right? So x, less than a, but now less than or equal to a. Now we're dealing with f of a comma b. So which means for random variable x, same, less than or equal to a. For y, less than or equal to b. Okay, and then a and b run through the real value numbers. All joint probability statements about x and y can, in theory, be answered in terms of their joint distribution function. For example, right, if we have this, x is from a1 to a2, and y is the interval between b1 and b2. So this would be f of a2, b2, right? Because this is x less than or equal to a2. B is b2, y is less than or equal to b2, plus f of a1, comma b1. Well, this is just part of this, right? Part of this one. Probably we better do this minus of this, minus, think about the minus of parentheses, f of a1, comma b2, plus f of a2 comma b1 minus f of a1 comma b1. Okay, if you think that way, it's better to understand this equation. This is just a simplified version of it. But this is just, you know, rewriting this. So for this, that's just f of a2 comma b, right? Can be split into this. As less than or equal to a2 can be split in x less than or equal to a1, and then x is in between of a1 and a2. Y, yeah, y less than or equal to b. So this only consider this first variable. Right. So we know this. This is f of a2 minus f of a1. Right. So everything comes from there. So same thing for this for y, right? For y. Same thing for the variable y. So this is a little proof of the statements before, all right? So that's why I was saying it's better to write the other way around. So there's a little p of x, y. So this is joint probability mass function of x and y. Before we have p of x. Now we have p of x comma y. So this is just probability of x and y. So the probability mass function of x can be obtained from the joint probability mass function by this. Px of x is the probability of a union of all those x and y's. It's a summation of all this. The summation of all these density functions. Right, evaluate according to this J. Similarly for y, we write as P y of y is a summation of all the density functions of P with the index. Okay, anyone has any questions? So everything from before, but now just putting those two variables together. But the idea is still the same. Let's see example 1. Suppose 3 balls are randomly selected from an urn containing 3 red, 4 white, and 5 blue balls. If we let x and y denote respectively the number of red and white balls chosen, then the joint probability mass function of x and y, P of ij, is obtained by noting that of the 3 balls selected, I are red, j are white, and the 3 minus I minus j are blue. Because all subsets of size 3 are equally likely to be chosen, so it follows the probability density function for this is out of 3 red, choose I of them. Out of 4 white, choose j of them. Out of 5 blue ones, choose 3 minus I minus j of them. Then divided by over 12, choose 3. Out of 12, choose 3 of them. So if we plug in some values, okay, no white, no red, no white, so we get 1 over 22. No white, no red, 1 white. While plug in, we get this. So on and so forth. So on and so forth. So this probability can most easily be expressed in table form, the reader should note that the probability mass function of X is obtained by computing the row sums, whereas the probability mass function of Y is obtained by computing the column sums. Because the individual probability mass function of X and Y thus appear in the margin of such a table. And they are often referred to as the marginal probability mass function of X and Y, respectively. Because it's 2 dimensions, so we can use row and column, right? So the rows, we have I goes from 0, 1, 2, 3. J, I is red color, J is white color, but also goes from 0, 1, 2, 3. Yeah. Anyone has any question? Okay, that's an easy example. Now let's see. So basically, you could think, and you could think, if you want to thinking further, right? This can be extended to n. It doesn't have to be only join 2 variables. You can join as many variables as you need. Let's see a second example. Suppose 15% of families in a certain community have no children, 20% have 1 child, 35% have 2 children, and 30% have 3 children. Suppose that in each family, each child is equally likely and independently to be a boy or a girl. If a family is chosen at random from this community, then B, the number of boys, G, the number of girls in this family will have the joint probability mass function, right? So if we use I representing boys, J representing girls, because there's at most three children, right? So the family, 30% have 3 children, and no family has 4. So from 0 to 3. So that's why each one, boys from 0 to 1 to 3, and girls from 0 to 3. Then we could calculate this. So basically, so this is an easy concept, right? Everything stays, you know, the calculation, anything is the logic is the same logic. No children, the 0.15 that's given in the question, 15%. And one girl, and a total 1 child. Right? And 1 child times probability, if it's only 1 child and the 1 child is a girl. So it's 20%. 20% of them have 1 child. And then if they do, what's the probability of the 1 child is a girl or boy? Is a half, 50%. So this one, 2 girls. So 2 girls and a total of 2 children. So 2 children, probability of 2 children multiplied by, you know, the families have 2 children, and also the 2 children are both girls. So that's 35% of them. 35% of them are multiplied by, of course, the probability of having a girl or having a boy is 50%. Let's see the third example. Consider independent trials, which each trial is a success with probability of P. Let X footnote R denote number of trials until there have been R successes. and let ys denote the number of trials until there have been s failures. Suppose we want to derive their joint probability mass function. So probability of x, r, y, s. To do so, first consider the case I less than j. Sorry, I'm thinking why they have to consider I less than j. Why do we even care I less than j? Oh, okay. All right, so that basically means success is less than the failure. Okay. So probability of x, r, y, s is the probability of x, r multiplied by probability if I success, given x success, and with j and j failures. So if there have been r successes after trial I, then there have been I minus r failures by the point. Hence, the conditional distribution ys, given that xr equals I, is the distribution of I plus the number of additional trials after trial I until there have been additional s minus I plus r failures. So then this can be switched to be this j minus, so the probability of y s minus I plus r equals j minus I. This is for success I less than j. xr is a negative binomial random variable with a parameter r and p, and the y s minus r I plus I is a negative binomial random variable with a parameter x minus I plus r and with a 1 minus p. So the preceding yields this. So remember the negative binomial random variable calculation. This is from there. We see that x and y are jointly continuous if there exists a function f of x and y defined for all real x and y, having the probability that for every set C of pairs of real numbers, so C is the set in a two-dimensional plane, so probability equals a double integral. Nice. So the function f of x comma y is called a joint probability density function of x and y. If a and b are any set of real numbers, then by defining C as a set, x in A, y in B, so we see the equation can be written as this: x in A, y in B, so integration over B, integration over A, double integrals. Because the cumulative probability f of A comma B equals to x goes from negative infinity up to A, yes, because x is less than or equal to A, y is less than or equal to B, right? So that means the integral has lower limit, upper limit. Then it follows upon differentiation, the density function, the f of A comma B, the joint density function, can be represented as second derivative of this f of A and B. Then the partial derivative, well, of course, whenever we have second partial derivative, it has to be defined. Another interpretation of a joint density function obtained is this: A less dA. So x is in this interval, y is in this interval. Then, of course, we have the interval to work with, the lower limit, upper limit of the integration of this. And this can be calculated as f of AB, dA, dB, about, approximate, nice. When dA and dB are small and f of x, y is continuous at AB, so f of AB is a measure of how likely it is a random vector x, y will be near YB. If x and y are jointly continuous, they are individually continuous, and their probability density functions can be obtained. So this is individually, right, for individual. Is thus a probability density function of x. So similarly for B. Interesting. All right, let's see this example. The joint density function of x and y now is given by this, right? So when x is positive, y is positive, so we have this density function. Otherwise, x, y are negative, that's 0. So we want to compute x greater than 1, y less than 1. And when x less than y, okay, this is interesting, B. And when x less than 8, okay, A and B, A and C are directed. So B is not so directed. B is x less than y. Okay, let's see. So A is x greater than 1, that's from 1 up to positive infinity. Y less than 1, that's from 0, because this defined from 0 up to 1. So we see y direction goes from 0 to 1, x direction goes from 1 from infinity. So we want to integrate the density function. Now, e to the negative x is e to the negative 1. So the rest is just calculation. The rest is just calculation. Okay, so the first one is easy, right? Let's say B, because B is x less than 1, x less than y. All right, x less than y. So y goes through from 0 to infinity, right? So that's the domain of y. Y, right? Y goes from 0 to infinity. And x is less than y. So x goes from 0 up to y. Because what is this? How do we interpret x less than y? Remember, x equals the y line, right? So under the line is x less than y. Hold on. Above the line is x less than y. Below the line is y less than x, right? So that's why you see this lower limit is 0, upper limit is y, because x less than y. Okay, so then integrate. All right, nice. Nice. All right, anyone has any questions? A is direct, only B. B takes a little bit of thinking. All right, let's see C. X less than A, right? That's easy. That's very direct. So 0 to A for x direction, 0 to infinity for y direction. Just integrate this. So 1 minus e to the negative A. I guess you will have homework. You can pick up some homework like this. Interesting to do. Let's see next one. Consider a circle of radius r, and suppose that a point within the circle is randomly chosen in such a manner that all regions within the circle of equal area are equally likely to contain the point. In other words, the point is uniformly distributed within the circle. If we let the center of the circle denote the origin and define x and y to be the coordinates of the point chosen, then since x, y is equally likely to be near each point in the circle, it follows that the joint density function of x and y is given by f of x, y equals c if x squared plus y squared less than or equal to r squared. So that means it's within the circle, the points are inside the circle, or on the circle, right? Basically on the disk, on this disk of radius of r. Otherwise, if fall outside the circle, it's 0, and for some value c. So we want to determine c, and we want to find the marginal density functions of x and y. And we want to compute the probability that d, the distance from the origin of the point selected, is less than or equal to 8. And we want to find the expected value of such d. Interesting question, huh? Let's go back to the question to make sure everyone knows what we're doing here. So just we have a circle of radius r, right? And just suppose a point inside the circle, right? And the point can be here, can be any quadrant, x, y. Is randomly pointed in such manner that all regions within the circle of an equal area are equally likely to contain the point. In other words, the point is uniformly distributed within the circle. So the center of the circle denotes the origin. So the center of the circle denotes the origin. And x and y are the coordinates. So since this point is equally likely to be near each point in the circle. All right. Okay. So now we want to determine this c. So we know, for any density function for probability, we have this, right? So it follows this. It follows the c such number multiplied by this, right? So this circle basically, right? The circle equals 1. So what does this mean? What does this mean? This means because this equals the c. So c times this area has to be 1. So which means we can evaluate this either by using polar coordinates or more simply by noting that it just represents the area of this circle. And it's hence pi r squared, right? So c equals 1 over pi r squared. Anyone has any question for this? Okay. B, we want to find the marginal density functions for x and y. Now we have this c, right? C equals 1 over pi r squared. So it depends on the radius of the circle. And the density for function for x is this. And it can be interpreted as this, 1 over pi r squared, the c, such c, right? With this only for one direction, because for x, we only have to calculate for y. And the calculation, so what is a? A is square root of r squared minus x squared, right? Because we're trying to find the within for x. And then we do the calculation. There's a 2 over pi r squared, square root of r squared minus x squared. And this x has to be, the x, y has to be inside the circle. Similarly for y, and it equals 0 when x squared greater than r squared. Right, that's outside. By symmetry, the margin density of y is given by, so this, right? For y squared has to be less than or equal to r squared. 0 if we false out. C, we want to see the, we want to compute the probability of D, the distance from the origin of the point selected is less than or equal to A. So the distribution function D, the distance, right, equals square root of x squared plus y squared, the distance from the origin. So obtained by, because A has to be inside the circle, has to be less than or equal to R. So we calculate this. That's for this is less than or equal to A. For the D, less than or equal to A. Right, that's means x squared plus y squared less than or equal to A squared. Then we can do the calculation, right? So double integration of the density function over the circle of radius A. That's 1 over pi r squared with this inside the radius, the area of the circle with the radius of A. And what's the area? Pi a squared, right? So pi a, so we have this times pi a squared. So we have this. Then just becomes a squared over r squared. Very interesting, right? Anyone has any question? Okay, last one, we want to calculate the expected value. So from C, we also get the density function D of A equals 2A over R squared. Because A is over X, right? So I have this. So to calculate the expected value of this, that's just FDA multiplied by integrate A squared from 0 to R. That's 2R over 3. Expected value. I forgot about this formula. So density function multiplied by the second part. Okay, if you have questions, you figure out this part, okay. Okay, let's see more examples. So joint density of x and y is given by this. F of xy is e to the negative xy. So for x and y being positive, 0 otherwise. So we want to find the density function of the random variable x divided by y. X/y. So we want to compute this for some a being positive. So that means x/y less than or equal to a. So that means the double integration of the density function in the region of x over y less than or equal to a. Very interesting. You see this interpretation, right? Very interesting. Because I'm working with it. Okay. So that means y, x over y. So y is going from 0 to infinity. Okay, this is right? 0 is not in the domain of y. But I guess this book just doesn't care much about the pure mathematics. So 0 goes from infinity. So y is being positive, right? So x over y less than or equal to a. So that means x is less than or equal to ay. All right. So that means x goes from 0 up to ay. Now to the integration. Integration in the end we'll get a 1 minus 1 over a plus 1. Okay, this kind of question is interesting. Right? This kind of question is interesting. So differentiation shows that the density function of x/y is given by f x over y of a equals 1 over a plus 1 squared, right? Because we yeah, we differentiate this one, because this can be simplified. This is a plus 1 over a plus 1 minus 1. So that becomes a over a plus 1. A over a plus 1. Then just, you can differentiate this. Then to get 1 over a plus 1 squared. All right. We can also define joint probability distribution for n random variables, of course. We can talk about the f of n variables. We can have 1 up to n. We can have up to n. Basically, we can have finite many variables, finite many joint variables. Let's see this. The multinomial distribution. So one of the most important joint distributions is a multinomial distribution, which arises when a sequence of n independent and identical experiments is performed. Suppose that each experiment can result in any of all possible outcomes with respective probabilities P1 up to PR. Yeah, because there are possible outcomes. And then, of course, adding all the probability has to be equal to 1. If we let xi denote the number of n experiments that result in outcome number I, then we have probability of this up to R as this, where adds up all these ni's that equals n experiments. Okay, so this is multinomial distribution. Okay, you can read this part to not so verify the little proof, words proof of this. Sorry. Let's see this. As an application of multinomial distribution, suppose that a fair die is rolled 9 times. The probability that 1 appears 3 times, 2 and 3 twice each, 4 and 5 once each, and 6 not at all is this. Very interesting, huh? 9 factorial divided by each 1 factorial, then 1 over 6 appear 3 times, appear 2 times, appear 2 times. So 1 appeared, the probability of 1 appeared 3 times, right? 2 and 3 appeared twice, then 4 and 5 appeared once, and 6 does not appear at all. Sorry, hold on, let me. Sorry, I'm teaching a class online right now. I'll call you back. Okay. Sorry, guys. So let's see this. So we can also use a multinomial distribution to analyze a variation of the classical birthday problem. which asks for the probability that no 3 people in a group of size n have the same birthday when the birthdays of n people are independent and each birthday is equally likely to be any of the 365 days of the year. Because this probability is 0 when n is greater than 730, we will, 730 covers 2 years, right? We will suppose that n is less than or equal to 730 to find the desired probability. Note, there will be no set of 3 people having the same birthday if each of the 365 days of the year is a birthday of at most 2 persons. Now, this will be the case if for any I less than or equal to n divided by 2, the event AI occurs, where AI is the event that 365 days of the year can be partitioned into 3 groups of respective size, I, n minus 2i, 365 minus n minus I, such that every day in the first group is the birthday of exactly 2 of the individuals. Every day in the second group is the birthday of exactly 1 of the n individuals. And every day in the third group is the birthday of none of the n individuals. So because each day of the year is equally likely to be the birthday of any individual, it follows for a given partition of the 365 days into 3 groups of respective size, that probability each day in the first group is birthday of exactly 2 of n individuals. So this is repeated. So then we get this, right? So can calculate it, n is how many people. Okay, as the number of partitions of the 365 days of the year into 3 groups of respective size. So we get this. It follows that probability of this. So then for probability of no set of 3 with the same birthday, when n equals 88, we can see an example. It's about 50%. Okay. Okay, interesting. Multinomial distribution, right? So this is multinomial distribution. All right. Anyone has any questions? Okay, I guess not. I'm going to